Chapter 3, Exercise 23. Let IA be the identity function on the set A. Show that for any sets B and C, the composition of B with IA is equal to the restriction of B to A, and the image of IA under C is equal to A intersect C. Okay. Let's do each one in turn. And these are just the usual proofs. So let's suppose UV is in the composition of B with IA. Then there exists some T such that UT is in IA and TV is in B. Now IA is defined to be the set of x comma x such that x is in A. So UT being in IA implies that UT is actually equal to U comma U, meaning that this T must be this U. So T equals U. Now this means that TV is equal to UV. So UV is in B and U is in A. Because UU and because we picked out UU from IA. So UV must be in B restricted to A. Thus, B composed with IA is a subset of B restricted to A. Now for the other way around, let's suppose UV is in B restricted to A. Then UV is in B and U is in A. And let's just observe that for all x, for all x, in A, XX is in IA. So U must be in IA, right? Thus, there exists some U such that U is in IA and UV is in B. Therefore, UV must be in B composed with IA. So, B restricted to A is equal, well, yeah, we can infer that by now, but must be a subset of B composed with IA. And now, for equality, we conclude that B composed with IA is equal to B restricted to A. There we go. Now part B, we have to show what the image of IA under C, keep getting that wrong, is equal to A intersect C. Again, inclusion going forward, we have suppose y is in the image of IA under C. Then there exists some x in C such that x, y is in IA. Note that xy being in IA implies that xy is equal actually to yy, and y must be in A. Or rather, well, yeah. Let's just say that this. So x equals y, and I don't like this. Okay. And thus y is in A. Yeah. No. Well, it's the same thing. Okay, whatever. But I think it's more correct to say this. Okay. So x equals y. And thus x being in C implies that y is also in C. So y is in A and y is in C. Meaning that y must be in the intersection of these two sets. So IA under C, the image of that, is a subset of A intersects C. Now, for the other side of the inclusion, this, and let's suppose, again, y is in A intersects C, and y is in A, and y is in C. Again, for all x in A, x is in IA. Thus, y itself being in A implies that y is in IA. So y is in IA and y is in C. So y must be in the image of A. Or rather, another way we can do this is show that y is in the image of A restricted to C. And note that y is in the range of the image of A restricted to C, and the range of IA restricted to C is actually equal to the set we wanted in the first place, right? So y must be in IA restricted to C. I mean, you don't have to do this step if you just know that these conditions mean that y is in this set, but in case it helps you, I'll just write it down. Thus, A intersects C must be a subset of IA restricted to C. Now for equality, conclude that the image of A under C is actually equal to A intersects C. And there you go. That's all of exercise 23. Hope this was helpful. I'll see you in the next video. Bye bye.